Yeah, just extending to our earlier portfolio kind of a framework, what we have seen as a part of the portfolio mean and variance kind of a framework till now is the entire risk of any portfolio we are measuring with respect to the mean and the standard deviation itself. So using that concept itself, we were able to arrive at the concept of value at risk, because for anything what we are saying is this is the average return of the portfolio and this is the deviation from the average. Now on the top of that, if I am able to add the distribution also, so this is the mean, this is the standard deviation, and this is following a normal distribution or some kind of a distribution, and that is what was the root cause for the computation of VAR. And when we have seen the above model, when we have computed the efficient frontier, this is how the efficient this part of it was the efficient frontier for us. And this is assuming that the returns are following a kind of elliptical distribution. As the risk is increasing, up to certain extent, the returns will come down, right? Again, on the other side, the returns are going up, which is like if I'm trying to find a graph for this distribution, it will be more like a parabolic or some kind of an elliptical, right? Probably it could, if I even look at it, it may come more like a parabola like this. So as long as, or probably if you look at it slightly like this is what is your normal distribution. So some kind of a curviness is present, and based on that is what we are trying to find out the VAR or any of the other aspects associated. Now what we are saying is this efficiency frontier kind of a framework which we have used earlier for measuring our risk adjusted return. If this is the risk, this is the return kind of stuff. If my distribution is not normal or elliptical and it follows some other distribution, some XYZ distribution, wherein probably it may come something like this. If my returns are following some other kind of a distribution, we cannot use the efficient frontier framework to typically find out the value that is at risk for us, or what should be the return associated with this amount of a risk. Because in those cases, whatever the standard deviation that we are measuring, it's not something accurate. And so from that framework itself is what we have arrived at the concept of VAR, wherein you typically find out the distribution, the underlying distribution, and you can very well find out the amount that is at risk. See, when we defined the VAR, what did we say? Whatever is the type of the distribution, it could be a negatively skewed or a positively skewed or something. I am putting a cutoff point, wherein whatever is the area in this cutoff point, if I say 1%, we call this as 1% VAR. What is this particular cutoff point? Where the area to the left of it, the chance of getting the area to the left of that cutoff point is the percentage, is the VAR percent. 1% VAR, when I say, it is nothing but that particular cutoff point in any distribution, right? It need not be normal, it need not be elliptical, any kind of a distribution. If I am typically finding out what is that cutoff point, what is that cutoff point which can break the data into the left and the right, and the left is around that 1% kind of, or 5%. When I say 5% VAR, the right of it is 95%, the left of it is 1%, and so on. So here the advantageous part of it is the return distribution. You can very well model it. So if you are not able to identify the return distribution, then VAR is not a good measure. But if you are able to identify what is the underlying distribution, all we are saying that the 1% VAR or a 3% VAR or whatever is the percent or 0.1% VAR, which we have used in case of operational risk and all in our earlier class. So what we are saying is, if this is the mean, and so mean plus z is assuming the based on the reliability factor, assuming a normal distribution. If it is some other distribution, the reliability factor will be something else. So based on the underlying distribution, and for how long you are looking at the var, daily var, monthly var, yearly var, what is the time period which we are looking, because the var will differ based on the time period of investment which we are typically looking at. And the var has a limitation in the sense it can compute this cutoff point, but it cannot compute this 1% will go to how long, right? Even if it has gone very narrow like this, even this area could be 1%. Or if it had gone only up to here like this, even this area could be 1%. So VAR has a limitation in terms of measuring the amount that is at risk. Only it will say cutoff point, that to the left of it there is only 1% chance, to the right of it there is a 99%. So there is only 1% chance that your loss will be more than this particular amount, but it will not say how much is that loss. That is one of the major limitation that was existing with value at risk, which we have discussed even in our earlier session also. One important thing, any risk measure, whether it is VAR or any other risk measure which we are looking at, what we need to see is in the graph, let's say some distribution, right? As we move to the right, the risk should typically come down. As the values are moving more and more to the right, the risk that is associated, the area that is on the left side. So what you are typically seeing as you are moving more and more, if your target is becoming more and more, or if your actual return is becoming more and more, or two different risks are there, where the amount of the first one is higher than the amount of the second. What you are saying is the return of the first one is higher than the return of the second. The risk wise, if you are computing the left hand side, let's say if we are talking about this particular process, this is X and this is Y, right? Which means the amounts which we are talking of here and here. So Y is greater than the X. But when we are talking about the risk that is associated with it, each risk, so the probability that my return will be more than this is this much, or my loss will be less than this. The probability that my loss will be less than this is this much. So what is found out, as we are seeing that we are going more and more towards this, the probability towards the right of it should typically come down compared to the probability towards the right of the one which is having a lesser X value compared to the Y value. That is what is the funda of monotonicity, which means each one is a separate risk in itself. As the value is increasing, the chance of having a loss less than that actually will keep decreasing. That is one fundamental of any risk measure. The second is what we are calling as a sub-additivity principle. Let's say I am combining X and Y. The standard deviation which is associated with X as well as Y separately versus combined, which we have seen as a part of our portfolio example. When I am combining two securities, even in our Excel sheet we have seen that when I am combining two securities separately, right, the maximum risk that was occurring in this example also, the maximum risk was 20%. which is this only, which means the combination, when I'm combining A and B, the combined risk is always less than or equal to the independent risk. That's the typical concept of the portfolio itself. And so any risk measure that we are looking at, whether it is VAR or whatever, so I am trying to find out the VAR of the first versus the VAR of the second. Add the two VARs, right? I am talking about VAR of the first versus VAR of the second. Add those two VARs versus find the VAR of the portfolio. What it is saying is the VAR of the portfolio should be less than or equal to the VAR of the two individual securities added together. That's the most important principle. Whether you are using VAR or next we'll talk about expected shortfall or any other kind of risk measures, or even in stress testing, whatever it is, whatever is the measure which we are using for computing the amount that is at risk, we are typically talking about the sub-additivity kind of a principle, wherein the VAR of the combination, the risk of the combination is lesser than the sum of the individual risks. And what is also saying is the risk associated with the same security, in the same security X, you have invested 2 times the money or 3 times the money or positive times the money. What it is saying is the risk is simply a multiplier. Right? If you have put 100 rupees or 200 rupees. If you have put 200 rupees in X instead of 100 rupees, the VAR associated with 200 rupees is double that of VAR associated with 100 rupees, as long as it's one single security itself, which is what is called as a positive homogeneity kind of a principle. It is homogeneous. As long as your focus is the same security, if your investments are getting multiplied, even your risk is also simply multiplied. It does not become squared or cubed or something like that. It is also getting uniformly multiplied across. That's the positive homogeneity kind of a principle. And to that security X, you are adding more and more funds as a constant value, not as a doubling, tripling kind of stuff, as a constant value. What it is saying is the risk of the security also gets added up with the constant value itself. So these properties typically are defining any risk measure you are trying to come out with, whether it is a VAR in this example, or it is the expected shortfall which we discuss in the next example, or it is stress testing, or it is any other risk mitigation which we are trying to deal with. These properties should be more and more applicable to those kind of measures which we are coming out with. And most importantly, the sub-additivity principle is the most important factor for any kind of a measure that is getting developed, which means when I am looking at the risk of A plus B taken together, it should be much less than or equal to, it cannot be greater than the risk of the individual securities put together. So, yeah, compared to the VAR, there is a lot of importance for another measure called expected shortfall. What this does is, see, in VAR, as we have already discussed, it talks about a cutoff point like this. So this is the point where 1% of there is a 1% chance to lose more than this cutoff, and 99% chance probably that my loss will not be more than that. But as we have already said, it does not tell me what is the average loss or what is the size of the loss. It says only there is only 1% chance that your loss can be more than this much. So that particular aspect has been overcome by this mechanism of expected shortfall. What it will do is, it will try finding out across all these layers. So probably 0.9% var, 0.8% var, 0.7% var. It finds out the var across all the layers and it gives a weighted average to each one of them, right? So there is a, so 0.9% var is something like this, 0.8% var is this amount, 0.7% var is this amount. So it gives some kind of a weightage to each one of them. What is that weightage? It gives a weightage of 1 by 1 minus alpha. Alpha is nothing but 0.9%. So 1 by 1 minus 1%, which is for 1% var, which is close to 1 by 0.99. And probably it will give 1 by 1 minus 0.9%, which is becoming 0.991 weightage. So 0.991 weightage is given to 0.9% var, 0.99 weightage is given to 1% var, 0.992 weightage is given to 0.8% var. Like this, it gives a different weightages and does a weighted average multiplication of them to arrive at what is the average size of the loss, right? So probably it's like this. Let's say when I'm talking about uh, a normal distribution with a mean of 5 and a standard deviation of another 5, right? Now 1% var for me, right? 1% var typically or probably 5% var, let's take. If I take a 5% var, I may say mean minus 1.96 times the standard deviation, or probably I may go with 1% var, which may go as mean minus 2.58 times the standard deviation. Like this, I will compute 0.5% var, 0.7% var, 0.2% var. Like this, I can compute any. Now, what we are saying is, if I want to find out the average size of the loss, so for this number, I will give 1 by 1 minus 5%, which is almost 1.05%, 1.05 weightage to this, and probably 1 by 1 minus this number. So which is almost 1.01 weightage to this. So based on this, what will I say? My average loss size is 1.05 times this plus 1.01 times this, and this is what I am saying, my average loss size is going to be around minus 13. The various weightages that uh, 1 minus this my average loss. So here I have to again make it to 1. This entire weightages which I am giving, I am making them equal to 1, which means in that proportion. So basically I'll take it as this divided by this plus this. In this proportion, I'll give a weightage. So here also I'll take this divided by this plus this. So in this proportion, so I will compute this times this plus this time, or probably I could have divided by the overall weightage altogether, though I have done 1.05. So probably otherwise what we could have done, this times this plus this times this entire thing divided by the summation of all the weightages. So I divide this by the summation of this plus this. So what this is saying is the average loss, in the tail is around 6.31. So expected shortfall is doing that kind of a job, which is where it is finding out the average size of the loss, not just, oh, this is the cutoff point beyond which there is a 5% chance of occurring. It is even computing what would be the average size of the loss, so that two different investments can be compared in terms of the average risk amount. So that is what we typically also call as a spectrum measure of risk, which is nothing but in this area, you are giving weightages to each one of the lines across, depending on the weightages which you are giving to each one, and doing a weighted average. If at all I want to find out the average amount of loss, normally if it is a normal distribution, we get this as the average amount of loss. How are we getting it? Probably it's as good as give different weightage to each of these and find out the average, weighted average. So the same concept is being extended even to your VAR, and that particular mechanism where each layer you are giving a different weightage and trying to find out the average of all these various combinations is what we are typically calling as a spectrum measure of risk, which means across the spectrum I can find out what is the amount of risk. Probably what is the 95% VAR, 99% VAR, 1% VAR, 5% VAR. Across the spectrum I can find out what is the amount that is subjected to risk. Now when we talk about VAR is a special case of the spectral risk measure, wherein the whole weightage is given only to this part. I am not bothered about all these things. That is what is VAR. Whereas when we are talking of expected shortfall, different weightages are given in this particular area, and a weighted average only of this area is being taken. So that's where what we say is both expected shortfall as well as VAR, both of them are special cases of spectral risk measure. So you have to really see what is the special case of both of them, because in case of expected shortfall, all these are given weightages of 0, and only these things are given a specific weightage in the computation of overall your expected shortfall. Whereas in case of VAR, only this is given a total weightage of 1. All these are given zeros, all these are given zeros. So that's the reason you will get with a one single value itself for VAR. That cutoff point comes out as one single value, which is nothing but expected shortfall for 1%. But we are talking of 1% whole of area. Then we are doing it for 0.8, 0.6, 0.5, doing a weighted average of all of them. That is what is coming out to the expected shortfall measure. So from this perspective, what we are seeing is the expected shortfall is a much better method of measuring the average size of the loss compared to a typical VAR measure.